Okay, let's talk about forces. So what is a force? The simplest explanation I could find is it's an interaction between objects that has a tendency to change motion. Now in mechanics, a force is a vector quantity with both magnitude and direction. And before we start, I'm going to assume that you can already resolve forces into vertical and horizontal components. If you can't do that, go look it up, come back in a bit. So the three forces we're going to look at today are weight, thrust, and tension. Now the first of those, weight, is a force that pulls downwards on all objects due to gravity. Now the basic rule here is that the larger something's mass, the larger its weight. Okay, and in all problems on Earth, gravitational force is the same. Okay, so we don't need to worry about weight changing on an object. It's always going to be a constant in a problem. The second one, thrust. Now if I push something, whether that be pushing something along, or whether that be the boosters on a rocket pushing it upwards and out of the atmosphere, it's a pushing force, right? It's in, well, thrust, we all know what it means. And tension, the last one, the one I'm most interested in today, is a force that exists inside ropes and strings, like this one here. It can be pulled, but it's also flexible. Now what that means is I can't push with a string. If I try and apply a pushing force to this system, the string collapses on itself, and there's no longer any tension in that system. If I let it back down and let the weight be supported by the rope or by the string, there's tension now back in that system. It's holding the object from falling to the floor. Okay, so it's in equilibrium, it's not moving. Now in mechanics, we describe objects like this as a particle, i.e. the weight is all in one place, or the mass is in one place, so the weight only has one point to act on. And the strings, we call them light and inextensible. Now what that means is we can ignore the mass, so there's no weight, and it won't stretch. So that's not going to be an issue in the problems we're going to look at. So a very simple problem. We've got a weight here, well, we've got an object here with a weight pulling it downwards and a tension pulling it upwards. Okay, and as you can see, it's not moving, it's not falling, it's not rising, so it must be in equilibrium. There are no forces acting in the horizontal plane, only the vertical. Now, if we're going to solve a problem where we have an unknown force, a tension, and at this point I've not told you an unknown force, the weight is 4.9 newtons of this object, we need to start with a force diagram. So I'll draw my particle, weight pulling it downwards, and tension pulling upwards. Now, have I missed any forces? There's nothing pulling to the left, nothing pulling to the right, so we're fine. There's no thrust involved here either. Now, if it's in equilibrium, it means that in that plane, in our vertical plane, the forces must be equal. So tension must be equal to 4.9 newtons due to the fact the system's in equilibrium. Simple problem, simple solution. So we're going to make it a little bit harder and try something a little different. Okay, I've changed the system. So now we've got our particle or object here being held by two strings. We've got one coming up this way and one coming up this way. So we've got two strings, and those strings will have separate and different tension forces. And our problem is going to be to try and work them out. Now, in a question, you'd be given some information. So I've already told you the weight of this is 4.9 newtons. So we're going to start on our force diagram with our object here. 4.9 newtons is the weight pulling it down. And we've got two forces of tension, one pulling upwards and one at a shallower angle, like that. And we'll call those T1 and T2, tension 1, tension 2. And I'm also going to give you the angles to the horizontal. Alright, so if I continue this line horizontally, I've measured them already. This one is going to be 80 degrees, and this one is going to be 30 degrees. And this is where resolving into vertical and horizontal components becomes useful. So we need to look at two planes. First of all, we're going to look at the horizontal plane, or H, horizontal, and we've got two forces there, or two components. We've got one pulling to the right, one pulling to the left, and they're actually these two lines here that I've already drawn. Now the way we resolve is with right angled triangles, as hopefully we already know. And we should know, because I'm dealing with the two adjacent sides to our angles, that this is going to be T1 cos 80 and T2 cos 30. Now, because that's in equilibrium, it's not moving anywhere, they must be equal. There's nothing else acting in a horizontal plane. So we can have T1 cos 80 must be equal to T2 cos 30. Then we're looking at our vertical plane. Now in our vertical plane, we've got two components acting upwards, one downwards. We've got these two vertical components acting up, and this one acting down. So these two added together must be equal to this one here. Now, using trigonometry again, we can define that as T1 sine 80 and T2 sine 30. So those two added together must be equal to 4.9. So we've got, and I'm just going to avoid these strings here, T1 sine 80 plus T2 sine 30 must be equal to 4.9. Now, I'm not going to go through the whole problem. This is a set of simultaneous equations using trigonometry. I want you to pause the video and have a go. As a hint, I would go about getting an expression from H, making T1 the subject, and substituting into the other equation. That's how I'd start it. But have a go yourself, and we'll come back in a moment. Done it? Fantastic. Okay, I'm going to go through the answers I got. If you didn't get these answers, go back, try it again. So tension 1, I'm going to give you to two decimal places. I had as 4.52, and tension 2, I had as 0.91. Those are both measured in newtons. And that actually makes sense when you think about this. If we're just trying to stop an object from falling downwards, because this one's more vertical than this one, there should be more tension in this string. And if I pluck them, I can always see, you might not be hearing it in the video, but I can always hear a note out of that string. This one, you should be able to see much looser. Okay, so there's less tension in that string. So it actually matches up to what we've got in real life, which means the maths works, which of course it does. Hopefully that gives you an idea of how to deal with problems where you need to find tensions in a system. They could reverse that, it could give you the tension, ask you to find the weight. But all this relies on it being in equilibrium, so the forces have to be equal, working in this case right and left, and in this case up and down. So have a go at resolving some forces involving tension and weight for yourself, see how you get on. That's it.